Hello, everyone. This is a presentation about zero knowledge proof. The content is generated by my team in Clear Cipher Lab. We plan to generate some easy to understand content in field of zero knowledge proof. And the first part is a start to talk about Growth 16. So the first lecture is an introduction about zero knowledge proof. I'm going to say what is zero knowledge proof first. So zero knowledge proof is a cryptographic method that allows some party that we called as prover to prove that I really know some kind of knowledge to another party that we called as verifier without sharing the exact knowledge to the verifier. Okay, now we want to overview some examples to better understand the meaning of the zero knowledge proof. So uh, you probably are familiar with the Veris Waldo puzzle. That's a well-known puzzle that's is a very big picture of a crowded place full of people. And the puzzle here is to ask the questioner to find someone that is called Waldo. So maybe this is not a very tough question. You may just spend some minutes and then search the whole picture and then finally uh, find the Waldo. But in concept of zero knowledge proof, the question is different. The question here is that how you can prove that you could find the location of Waldo without leaking the exact location to us. So maybe you ask that why this is matter. So yeah, maybe we want to give the chance to other questioners also to think and try to find the Waldo. And that's the reason we expect you to prove that you found the location of Waldo without leaking the exact location. So this is an example of zero knowledge proof. I mean, we expect you to prove that you could find the location of Waldo without showing the exact location to us. So that's a zero knowledge proof example. Okay, so now we want to introduce a protocol that provide this question. Okay, the protocol says that we can have a very big and black curtain that there is a very small hole on this curtain. And then we ask from anybody who claimed that who could find the Waldo to go back to this curtain and try to show the Waldo from that hole. You see, right now, seems that somebody is trying to show Waldo from that small hole. Yeah, and this is Waldo, right? So this is, uh, let me bring the pen. Yeah. So this is Waldo that is shown exactly from the hole. We can see that the prover actually found the Waldo, and this means that he really knows the exact location of Waldo. But we, as the verifier, we cannot distinguish the exact location, right? So this means that the prover could prove something without leaking the details. Okay, so in concept of zero knowledge proof, we expect three main properties. So the first one is zero knowledge. So this means that the verifier could be convinced that the prover knows that knowledge without getting any information about that knowledge. Like in the Veris-Waldo puzzle, we convinced that the prover actually found the location, but we couldn't distinguish that what is the exact location of the Waldo on the picture. So this kind of proof is zero knowledge, right? So the second property is for the proof side. So that's completeness. So completeness says that if a statement is true, so then the verifier should be convinced that this proof is correct. So proof should be complete to convince the verifier that, yeah, the claim is correct. And the third property is soundness, and that says that if the prover doesn't know the exact knowledge, he could not be able to convince the verifier, right? So the current protocol that we have designed for zero knowledge proof of the location of Waldo possesses these three properties because this is zero knowledge, because we just convinced that the prover knows the exact location of Waldo, but we could not distinguish the exact location. And also the protocol provides completeness because if the prover really knows the exact location of Waldo, he could convince us because he could show the Waldo from that little tiny hole. And the third property is soundness because the prover could not convince us if he really doesn't know the exact location of Waldo, because if he doesn't know, he could not show the Waldo from that small hole. Okay, these three property, all the ZKP system should possesses these three properties. So in fact, all proof system should possesses these two property, right? So any kind of proof should guarantee committedness and soundness, and zero knowledge is an extra property to provide zero knowledge kind of proof. Okay, so the first example was an easy to understand example about zero knowledge proof. And now we want to discuss another zero knowledge proof protocol. Okay, suppose that we have two very similar balls. So they are completely at the same size and the same weight and the shape, but the colors are different. So one ball is green and the other ball is red. So now we have a guy called Victor, which is colorblind eye guy. And also we have Peggy that decided to prove to the Victor that the color of these two balls are different. So since Victor is color blinded, he could not distinguish the color by looking at the balls. So now we want to design a zero knowledge proof protocol that allows Peggy to convince Victor that the color of the balls are really different. Okay, here is the protocol. So the protocol asks the Victor to hide the two balls behind himself and decide to choose the location of the balls or not. So for instance, Victor decide to change the location. Now the green ball is on the top and the red ball is down. And bring the balls again in the front of himself and ask the Peggy to say that if he changed the location of the balls or not. And if the color are really different from each other, Peggy could distinguish from the color that the location are changed, right? Because at the original step, the red ball was on the top, and now Peggy could see that the green is on the top. So then Peggy could distinguish that their location is changed. And Peggy just distinguished this by watching the different colors. So if Peggy could say the exact answer that if the location is changed or not, so Victor could be convinced that, okay, it seems that the color are really different. But the problem here is that the probability of correct guess is 1/2 because if even the two balls they do not have different color and the vector change the location, Peggy with probability of 1/2 could say the correct answer randomly, but just say switch or not switch. So that's the reason Victor could not be convinced by just one iteration because the probability of correct guess is 1/2, and this means that the soundness error is high. Is over 2. Soundness error means that there should not be any easy way for the prover to convince the verifier when the prover doesn't know the knowledge. Okay, so the protocol says that if the verifier repeat this process again and again for k time or for n time, and then for any iteration, Peggy could say the correct answer. In each iteration, Victor randomly decide to change the location of balls or not. And if Peggy says the correct answer about change the location or not, after multiple iteration like n, so then the probability of correct guess would be 1/2 to the power of n. And after enough n value, so then we can say that, okay, the color of the balls are really different from each other. Okay, so after n times, so then the probability would be 1/2 to the power of n. Okay, so such a protocol again had the three property, the zero knowledge proof property, because Peggy doesn't leak the color of the balls to the victor, right? She just says that if the location are changed or not, and after n iteration, Victor could be convinced that all the color are really different from each other. So, and also the protocol provide completeness because if the color are really different, Peggy could convince Victor. And the protocol provides soundness because if the color are not correct or not different, so Peggy could not convince the victor because the probability of correct guess is 1/n, and after n iteration is not easy to just say the correct answer if the color of the balls are not different from each other. Okay, so we started with Verisbaldo example, which was a very easy ZKP example, and then the color of the balls, which is a little complex than the Verisvaldo. Now we want to go and discuss a third example that consists of some mathematics. So the question here is that what is the square root of y when the value of y is known? So we want to follow a protocol that allows zero knowledge proof for this puzzle, but we want to rehearse this protocol with very small values to be easier to understand. So that's the reason we have choose the value y equals to 49 and the square root is 7. So here the puzzle is that the value of y is known by the public, and the question is that who knows the value of a square root? So at the first glance, this is not a complex puzzle, but when we work in modular arithmetic and with big mod values, so that would be a very, very tough question. So finding a square root of a value is not easy at those finite fields. So, but for simplicity, we just want to work with small values to just track the protocol. Okay, here the prover claims that I know the square root, but I want to convince the verifier that I really knows the square root. And I don't want to share the square root to the verifier. To provide this puzzle, an algorithm is designed. So the algorithm consists of different protocols. So the first one is the commit. So the commit algorithm says that the prover need to choose a random value like r and then send r to the power of 2 to the verifier. So the protocol then says that at the second round, the verifier should pick a random value like b equals to 0 or 1 and send it to the prover. So then there is an evaluation algorithm on the prover side that says that if the value of b equals to 0, compute z equal to r, and if the value of b received from the verifier equals to 1, compute the value of z equal to r multiplied by the square root of y. And then send the value of z to the verifier. And at the verifier side, there is a verification algorithm that says that you need to compute z to the power of 2 and check that if it's equal to r to the power of 2 multiplied by b to the power of y, b to the power of b, sorry, y to the power of b. And if they are equal to each other, and then the verifier would be convinced that the prover really knows the square root of y. Okay, so you may ask that how you can guarantee this protocol really works and provide completeness or provide soundness. So soundness means that how you can guarantee that if the prover really doesn't know the square root, then the equality test on the verification algorithm would not be passed. So that's the soundness proof of such a protocol that consists of mathematics, and we don't want to overview those proof to prove that this protocol really works. We just want at the first step, we just want to track and review this protocol to see that how it works. Okay, so for the chosen values that y equals to 49 and square root of y equals to 7, we want to follow this three algorithm to ensure that this protocol really works. Okay, at the first step, the prover send a value like r equal to 8, and r to the power of 2 equals to 64, and send 64 to the verifier. So then verifier choose a random value equals to 0 or 1. For instance, we assume that verifier pick b equals to 1. And now, since b equals to 1, the verifier, the prover, should compute z by this formula. So the prover will compute z equals to r multiply the square root of y. So the value of r is known by the prover already. So this is this value. And then the value of square root of y also known by the prover. So therefore the prover could compute r square root of y, which is 56, and then send 56 to the verifier. Now at the verifier's side, the verifier should check this equality test. First, the verifier computes z to the power of 2. So since z equals to 56, so then z to the power of 2 equals to 3136. And also the verifier should compute r to the power of 2, which is received from the first step, right? And multiply by y to the power of b. So b is a value that's already picked by the verifier, so verifier knows it. And y is a public value, right? So y is a public value, so which is in the puzzle, it is mentioned that it is known to the public. So since verifier knows those values, could compute the right side, and the right side also equals to 3136, and the left side and the right side are equal to each other. So by this example, we follow this protocol, and we distinguish that the verification test is passed. So then the verifier is convinced that the prover really knows the square root of y, right? So here, the prover doesn't share the square root of y with the verifier, right? So then you can say that this is a zero knowledge proof, because the prover could convince the verifier that I really know the square root of y without leaking what is the exact value of a square root of y. And also the protocol is providing completeness. So this means that if the prover really knows the square root, the verification algorithm should be passed, which in our example, it is passed. And also the protocol guaranteed the soundness, which means that if the prover doesn't know the square root, then should not be able to convince verifier. For instance, if in this example, the prover doesn't know the square root of 49 is 7, and let's say the prover assumed that this value is 6. And if you replace the square root by 6, so then the verification algorithm should not be passed. So, and if it's not passed, so this means that the soundness also is guaranteed. Okay. Yeah, as I said before, finding the square root is a hard problem when we work in modular arithmetic with big values of mod. Okay, so let's compare these three examples of zero knowledge proof. The first one, Veris Waldo, the second one, the color bold, and the third one, the quadratic result. Okay, the first criteria, we want to think about the iteration. So we see that the Veris Waldo puzzle, it was not an interactive protocol. There wasn't any interaction between the prover and the verifier. The prover just went back of the black curtain and tried to show the Waldo from that tiny hole. There wasn't any interaction between the prover and the verifier, right? In the second puzzle, the color ball, there was an interaction between the the prover and the verifier. So the prover, the verifier hide the color back of him and then decide to switch their position and then bring in front of him. And then the prover reply that if the location is changed or not. And this step is repeated for n iteration. So then there was an interaction between the prover and the verifier, and we call this kind of protocol as interactive ZKP system. And the quadratic residue also, it is an interactive ZKP protocol because the prover first sends something and then verifier pick value for B between 0 and 1. And then the third step, the verifier send the value of Z to the verifier. So this interaction says that this is an interactive protocol. Okay, the other criteria is the meaning of knowledge. So in the zero knowledge proof, the term of zero knowledge refer to different kind of knowledge. So if you go back to the first definition of zero knowledge in the first slide, so we mentioned that a zero knowledge proof is a cryptographic method that allows someone to prove something that they know something or they know some knowledge. So in different puzzles, the meaning of this knowledge is different, right? In the Veris-Waldo puzzle, the knowledge is the exact location of Waldo, because the prover wants to convince the verifier without sharing the exact knowledge of Waldo. When we say that this is a zero knowledge proof protocol, knowledge here is that the exact location of Waldo, and the prover wants to hide that knowledge. In the color bold puzzle, the knowledge is the exact color of balls. The prover doesn't want to share the color of balls to the verifier. The prover just wants to convince the verifier that the color is different. And in the third puzzle, the knowledge is the square root of y. So the prover wants to convince the verifier without sharing this knowledge, this square root of y. And here, this is the knowledge that should not be shared. Okay. So now we want to talk about two general categories of ZKP system: the custom design ZKP system and general purpose ZKP system. Okay, so the first one is the custom design ZKP system. Those are kind of ZKP system that they are designed for a specific puzzles, like the protocol that we designed for the Veris-Waldo puzzle, and then the protocol that we designed for the color ball puzzle or for the quadratic residues. There are some other examples for other puzzles also, and each of them, they have some custom design and specific protocols. So these protocols, they are efficient for that a specific task, right? For instance, the protocol that we have designed for Veris-Waldo, that is very efficient for that specific puzzle. But they could not be used for the other puzzles. For instance, the protocol that we use for Veris-Waldo could not be applied for the color board, right? So we cannot ask the prover in the color board puzzle to go back to the curtain and try to show the balls from that hole, right? So the protocol that is for Veris-Waldo is just for Veris-Waldo. The protocol that is designed for the color board is just for the color board, and it is not good for the quadratic residue or other puzzles. So these custom design protocol, they are just designed for that specific puzzle. For that specific puzzle, they are very efficient. But the problem here is that they are not reusable for other puzzles. But the problem here is that in the real world, we have so many puzzles, maybe billions of puzzles. We may prove to many kind of puzzles to the verifiers without sharing knowledge. We cannot design that custom design specific protocol for all of those different puzzles. And those puzzles, they are more and more complex than these three puzzles that we overuse. So that's the reason, other than the custom design protocol, we have general purpose protocols. The general purpose protocol, they are just one specific protocol that could be reusable for other kind of puzzles. So any kind of puzzle could be applied for those general purpose puzzles. For instance, if we have a general purpose puzzle, we can prove we know the correct answer of a Sudoku puzzle to the verifier without leaking the correct answer. Or we can prove that we have a specific age when we are using some specific application without sharing the exact information. Or we can prove that a specific grade is received by the number from some referees without leaking those specific grades. So this is an example that in next lecture we will focus on this example to see how Gross 16 as a well-known general purpose ZKP system works. Okay, so now we see that if we could be able to design a general purpose ZKP system, it is not efficient for any puzzle, but at least it provides a zero knowledge proof for any kind of puzzle. And there is a theorem here is that it says that if there are one-way function, so then every L in NP has computations, zero knowledge, interactive proof system. And we know that there are one-way function in cryptography. So then using cryptography, we are able to design general purpose ZKP system. And many of the research in the field of ZKP these days is focused on designing a different ZKP system like Gross 16, Plonk, Halo 2, and others. And this part of the lecture, we want to see how Gross 16 is working. ZK Snark also is one famous branch of ZKP systems, and that stands for Succinct Non-Interactive Argument of Knowledge. Succinct means that the size of proof and the verification algorithm is cheap, and non-interactive means that there is no interaction between the prover and the verifier, like the Veris-Waldo puzzle that was non-interactive, and argument of knowledge is meaning something like proof. Okay, for the first part of this lecture, we want to focus on Gross 16 as a general purpose ZKP system. And this is the general architecture of ZKP of Gross 16. So you convert the puzzle and you gives the puzzle as an input to this Gross 16, and the output you received a proof. For instance, if you want to work on Sudoku puzzle, So this means that as a prover, you claim that, hey, I know the correct answer for this blank cells in the puzzle. For instance, I know that this is 7, for instance, this is maybe 2, something like that. I know the exact answer, but I don't want to share the exact answer to the verifier, but I want to prove that I really know the exact answer. So Gross 16 allows you to convert your puzzle into something and then gives this puzzle to the ZKP system, the Gross 16, and then in the output you will receive a proof and then send this proof to the verifier, and verifier run a verification algorithm to be convinced that this is a correct claim. So inside Gross 16, we have different steps. First, we want to convert the puzzle into a constraint system or into a circuit. For any kind of puzzle, the Gross 16 will convert the puzzle into a circuit. For the Sudoku puzzle, we have a circuit or constraint system. For age verification, also, when we follow the protocol, we will have another different circuit or constraint system. Then we will use another transformer to convert the constraint system or the circuit into a matrix. And then we use the third transformer, which is Lagrange interpolation, to convert the matrix into polynomial. And then we convert the polynomial using the equality test and pairing to something which is the proof. And then send the proof to the verifier, and the verifier will check the verification algorithm to ensure that this is a correct proof. For each of these different parts, like the converting circuit into matrix, or converting matrix into polynomial, or the equality test, or the pairing, we have different lectures first, sorry, to explain what are these preliminaries. What is pairing, what is equality test, what is Lagrange interpolation, what is constraint system. We will discuss these different concepts in next lectures, and then in the final lecture we will completely understand how the Gross 16 is work. So the whole Gross 16 consists of those small features and the small technologies that we will discuss in next lecture. Okay, thank you so much. In the next lecture, we will start the first preliminaries for the Gross 16. Thank you.